first of all, it's a little odd here being a lead speaker to a battery conference. I started in batteries maybe a decade ago, playing with my little pinky, but maybe parts of 2 fingers now, but that's about it. But since I'm talking to a bunch of real battery experts, I thought it would be more useful if I talked not about stuff you know about much better than I, but the surrounding system that one would need for batteries in EVs. And so let me start by looking at the projections people have been making. I'm sure you know of these. This happens to be by Bloomberg New Energy Finance. And they're looking at the projections of electric vehicles. They did this projection in 2019. And you see here in 2019 where the different colors of different countries, blue is US, red is China, yellow is Japan, and so on, that the growth of EVs going to 2040 is expected to be quite large, and in terms of fraction of new cars sale by 2040, I've heard things ranging from 30 to 60% of all new car sales might be.
Can you use the?
Aha.
Okay.
Okay. Sorry about that. I'm looking at my computer. Okay. Anyway, going back to this. This is the projection for 2040. Somewhere between 30, 40, 50, maybe 60% of new car sales are expected to be EVs. Okay. Great. Okay. So if you break that down into countries, there's something else going on. If you see, Norway is 90% EVs because the electricity is free and many other things about Norway, and so the orange and blue, the dark blue are plug-in hybrids, and the orange are battery vehicles. So China is now 40% and still growing. The others are slowly catching up, but the question is, are these trends really real, and what's going to happen? Going back to the very optimistic trend over here, is this really going to happen? All right, so I then point to another article that I found recently. Instead of the 2019 projection that I showed you just a while back, I'm showing you now Bloomberg New Energy Finance for April 2024, and it's essentially saying that last year, in 2023, there were 950 gigawatt hours globally of lithium-ion batteries split between EVs and utility-scale storage. And by the end of 2025, they're saying there's going to be manufacturing being built up that could produce 7,900 gigawatt hours worth of lithium-ion batteries. But the projections they're now saying are 1,600 gigawatt hours. So this is what I was referring to. If you're entering into a battery startup company for the next couple of years, you're going to be doing R&D and not much sales. And so then the question is, and when you see this overproduction, it's profound overproduction, and it was like that with solar photovoltaics, and as a result of that, the biggest solar photovoltaic company in Germany went bankrupt. A few in the United States went bankrupt, including one called Solyndra. They got a federal loan, and then I was punished for the rest of my stay, Secretary of Energy for Solyndra, even though it was picked by career people in the previous administration. Never mind that. But the biggest PV company in China also went bankrupt, Suntec. Okay, so the difference is in the United States, it becomes political fodder, and the president and secretary of energy are punished. In China, they just prop up the company until the market figures itself out. So I'm not sure what's going to happen with batteries, but I suspect this might also be repeated, that there's tremendous innovation going on in these companies. It's fantastic in all the companies. It's not flowing from, let's say, the United States outward. I'm on the board of a battery company called Amprius, and a very high silicon content battery that would, if this company does survive, it will survive on that battery because it's very manufacturable and can get 400, 450 watt hours per kilogram in something that's inexpensively manufacturable and lasts a long time. But it remains to be seen. That was invented by engineers in Nanjing, not in the Bay Area. So, but moving on along, this is my abstract that I wrote, and what I was really saying, it's just about a few words, so I'm going to move on. And there's so many reasons why things are beginning to stall in batteries, and the most striking of all those things is the charging. When you are an early adopter, you don't really care about that. You know, this is important for the planet, I'm going to do this. Once you get past the early adopters, and when you're starting to get 20, 30, 40% of the new car sales being EVs, it has to be mass marketed. Okay, so this is a projection of EV battery demand by various things. You might notice something. It's a time between 2020 and 2030. And these are various studies, Rollenberger, BMO, BNS, S&P Global. The blue dots, so I just said I can play this game too. I can put, this is a diagram of projected EV battery sales, 2020 to 2030. And this is in thousands of gigawatt hours. The different colors are different forecasters, and I decided, since they're all over the map, I said I want to check, as a fact check, I'll make my own forecast. My own forecast simply means I ask Perplexity, what will be the market in EV batteries 2021, 22, 23, 24, and those are the blue dots. So large language models don't do a bad job if no one else knows what's going on either. So it is all over the map. For sure, I think it is going to be an issue. All right, so moving on, I'm going to give you a brief history of the history of electric automobiles. I'm a big history fan, and sometimes when you study history, you can learn a lot about things. And in the caption it says, those who don't study history are doomed to repeat it. Yet those who do study history are doomed to stand by helplessly while everyone else repeats it. So, in any case, I take this lesson to heart, that it is nice to look at history and how, and especially we're looking at history of a technology change that requires a complete support system and infrastructure. And so it's just not a new widget like a smartphone. Very, very different. You buy a smartphone, it's okay. You have the plugs, you have everything else. This is very different. And so let's move on to this history. The first automobiles were not gasoline powered. They were electric. And so Thomas Parker invented the first electric car in 1884. There in the middle you see a German electric car in 1904. And if you look at that car, it looks like, hey, this is amazing. It kind of looks like a carriage that horses pull. And all they did is they take off the harness from the horses. The driver is still on top. But and then Edison gets in the game by 1913. So these are first electric cars, and they were pretty good. The interest in electric vehicles was good. The vehicles didn't have vibration, they didn't smell, they were noisy compared to gasoline cars. They didn't require gear changing, and so gear changing. Remember that a long time ago, all you old timers. You know, would say, okay, I'm going to teach my kid how to use the stick shift. Those are the good old days. But anyway, so the electric cars didn't have none of that, and Henry Ford's wife, Clara Ford, actually did not drive a Model T. She didn't like it. It was dirty, it was smelly, and so she drove an electric vehicle, which is kind of amazing. She did change eventually. Okay, but so in 1900, 38% of the American automobiles were electric, 40% were steam-powered, and 22% ran on gasoline. And by 1912, the whole thing changed. Okay. So you have at the very beginning, first electric vehicles, the steam-powered were quickly going to lose out. This is burning, I don't know, petroleum or coal or something. Literally a little steam engine in the back that wasn't going to make it because of the smell and everything else like that. But anyway, so the big breakthrough was the Model T. The specs of the Model T were pretty impressive. It had a 177 cubic inch, 3.9 liter engine. It cranked out 20 horsepower at a top speed of 42 miles per gallon, a 10-gallon tank, and it's pretty economical. It was not a powerful car, so it would get 13 to 21 miles per gallon. So the range was 150 miles. That range, by the way, was immediately double the range of the better EVs that were in process. So, and the EVs, by the way, were lead-acid battery charged. And so if you think the charging today is slow, think about charging a lead-acid battery. Okay, so this first Model T cost $780 in 2010, which was equivalent to $25,000 today. So the first Model T was like an inexpensive internal combustion engine car. But Ford was really insistent on improving the efficiency of manufacturing. He introduced lots of things, assembly lines, things like that. And by 1924, it dropped to $290, which is $5,000. Those prices were amazing. And this completely undercut the electric vehicle market. And in fact, it revolutionized the entire car market. Because before Ford, there was Benz, Volkswagen, and Peugeot, and all these other things, and they were double and triple the cost. So it was this invention that really changed the world. And to tell you how serious Henry Ford was in driving down costs, this is the cumulative number of shipments. It goes from 10,000 to 100,000 to a million to 10 million, and the y-axis is the cost. And so this is plotted as a logarithm on both axes, the so-called famous learning curve. And someone shouts there, should say next slide. And so, so in any case, he sold 15 million Model Ts. And in doing that, he really drove the price down. And so it's a really remarkable, totally vertically construction of these cars. They made their own paint, they had their own steel, they had their own everything. Okay. All right. So if you look at a list of what happened, why did gasoline-powered cars take over from the automobile market so rapidly? In less than a decade, boom, it was gone. The show was over. Greater range. As I said before, the good EVs, a lot of lead-acid batteries, had an 80-mile range. Model T doubled it. Rapid development of gasoline infrastructure. So the first filling station was actually developed in 1913, and by 1929 there were over 121,000 filling stations. New York had over 1,500 filling stations, and Manhattan had the lion's share of those. So let's say at least a third of all the filling stations. So there was a filling station every square mile. Okay? It's a filling station every square mile, but you only needed a couple of minutes to fill. And so suddenly, and oh, by the way, no government largesse in this one. Nothing. It was so profitable that these things started popping up. And so that became very good. I've already talked about the price. When you're in rural areas, and this is, you know well in places like Canada, if you're outside the city, Montreal, Toronto, Vancouver, you know, there's wide open spaces. and you want longer range. Also, at that time, the internal combustion engine, the Ford, had a more powerful engine, so they could do rough roads. And the other thing is that these lead-acid battery cars didn't start well in wintertime and cold weather. The automobiles also didn't start completely well, but they were okay. But then something else happened. What killed the electric car was the electric motor, in part. Because in the good old days, you had to hand crank like this. Right? You've seen old movies for both airplanes and cars. And then when the electric starter came along, suddenly women were willing to drive the car because they didn't have to hand crank it. And it became much more convenient. And so by 1912, electric starters were, and so that single invention really made things say, okay, the last little lesson why you would want an electric vehicle is gone. So if you look at all these things, what has changed today? Not much. These are still the advantages of an internal combustion engine car or an EV. Anyway, this is the evolution of filling stations. In the upper left-hand corner, you would buy your gasoline at a drugstore, at a blacksmith shop, at something like that, and in 5-gallon cans. And then in the lower left-hand side, there's the first few pumps. This is a more modern pump, and so you have these gas stations now having not 2, but 3, 4, 5, 6 pumps in a single gas station. Again, rapidly going on in less than a decade, this proliferation of gasoline stations. So, to make it even more dramatic, this is a picture, Easter morning, 1900, Fifth Avenue, and there's one motorized vehicle. Go to 13 years later, Easter morning, Easter parade, 1913, and you look around, there's all cars, and you can find one horse-drawn carriage. Now, what's the difference? This transition to automobiles required this complete oil gasoline supply chain. It required better paved roads. It required repair shops. It required everything. And so how can it change so much in a decade or a decade and a half? And the answer is the transition to automobiles was driven by a very serious environmental problem. And that environmental problem was that there were 160,000 horses in New York in 1880 producing 3 to 4 million pounds of horse manure a day. And so people were ankle deep in horse shit in Manhattan. And so this had a big effect. It's actually having an effect in heavily populated areas. This is a picture in India, New Delhi, and it's smog. And we're found out that PM 2.5 is particularly deadly. This is particles less than 2.5 microns. And large studies are showing that for every 5 micrograms per cubic meter of PM 2.5, there's an 18% higher chance of getting lung cancer. And so it's also estimated that the average air in Delhi is 122 micrograms per cubic meter. 5, remember, gives you an 18% higher chance of lung cancer. And so this is not a good number if maybe 11 plus percent of people dying in Delhi are dying because of PM 2.5. So this is let me go back. So, and it turns out lung cancer is not the most serious disease you get from PM 2.5. It goes heart disease, stroke, lung cancer, then COPD. All very, very nasty. All right, so in any case, here's this. So this is just the thing of most polluted cities. Don't want to go into that. So let's compare the filling stations. Just to repeat, in 1913, the drive-in filling station was first introduced by, in 1929, this is 6 years later, 120,000 filling stations, of which there are 2 to 4 pumps. So you multiply 120,000 by 2 to 4, you get a big number. You look down here, I forgot to raise the print, but in 2024, in the United States, there were 183,000 charging ports, of which there are really fast chargers, 43,000 really fast chargers. But the difference is just not the number, it's the time it took to fill up your car or charge your car. And so if you look at this, for example, Tesla says you can charge, and if they're super fast chargers, you can charge 50 minutes of charge can give you, I think 200 miles, roughly speaking. But there are some fast chargers available. But still, if you fold in the time it takes to charge and the fast chargers compared to the filling stations, even in this very short time, it's still like night and day, even though the U.S. government is pouring lots and lots of money into this now. Okay, so I'm going to skip this. This has to do with challenges and opportunities towards fast charging. This article goes into some of the, it's a review article written by Yishui and his two members of his group. This first graph is just saying if you're charging at a certain level, level 1, level 2 DC fast charging, and so on, how long it will take. The article goes into all the many failure mechanisms that you have to overcome, specifically, as I said before, the resistances, how do you eliminate them, how do you get those things. But I'm going to move on, and let's see, just compare more graphically, yes. Compare more graphically the number of charging stations and filling stations. And so in the United States, this rapid deployment of filling stations, you had roughly 1,000 cars per pump. The actual ratio of charging stations to EVs per pump is not bad. And if you can do it in 5 minutes instead of an hour, it's a totally different thing. And so that's really the issue going on here. How are you going to get this to fast charging? If you could get fast charging to be, as I said, 6-7 minutes to do 200 miles, then all of a sudden you go back to the service station model, the number of chargers goes way down. And the amount of real estate for that goes way down. So that is really a major part of EVs being accepted. So what are we up against? This is a plot of energy per unit volume and energy per unit weight. Is what you see all the time in batteries. And leading the list is diesel, gasoline, kerosene, and fat oil has a tremendous amount of energy. Tremendous amount of energy in those things. That's where today's batteries are. It's pretty close to the origin. And you have to convert megajoules to kilogram, to whatever watts per kilogram. But now the electric vehicle is 3 times more efficient, roughly. So you can move that over by a factor of 3 up towards that. It's still way, way different. And as I pointed out in the discussion, the energy content of a gallon of gasoline is about 1.3 times 10 to the 8 joules, 125,000 BTU. Corresponds to 22 megawatts at 10 gallons a minute. So you're pumping a pretty slow rate. You've got a 20 megawatt conductor. And so an internal combustion engine car gets 30 miles per gallon, you get 300 miles in 2 minutes. Okay. We can get, I'm pretty confident people will be willing to accept, 200 miles in 5 minutes. And because so many other things are good about electric vehicles. So this is again a chart of where batteries are, different ones, starting with lead acid, going to zinc, lithium ion polymer, things like that. I think we're going to probably be here in maybe 5 years. I only know this because Amprius is giving out samples with those specs to manufacturers. So getting to be over 400 kilograms per watt in a manufacturable battery and high volume. Also very good news is that there's been a spectacular drop in batteries. Again, this is learning curve, so the x-axis is number of shipped battery megawatt hours, and the y-axis is cost. And you see that it's plunging very, very rapidly. By the year 2000, there were $2,000 a kilowatt hour. By 2020, $100 a kilowatt hour. These are manufacturing costs. And by 2030, probably less than $50 per kilowatt hour. So the question is, we talked about this before, are there going to be materials resource problems? And the answer is maybe, but let me go back. We mentioned nickel and cobalt, already a shift to iron phosphate. Now the idea is to improve the iron phosphate mixtures to make them better, because you're sacrificing energy density. But going back to this, this is some more. This is Chang Lu, who's an assistant professor at the University of Chicago, a graduate student at East Way, a postdoc of mine. And when she was in my group, she did first work on how do you extract lithium from salty water like seawater, and further work she can start with seawater. One lithium ion, 20,000 sodiums, and she gets 8-to-1. Whether this is commercially viable, I don't know, but there are other methods that are becoming commercially viable. So you suck up the salt water, take out the lithium, pump the salt water back. Cat's meow over, so I'm going to have to hurry up. The cat's meow is lithium metal sulfur batteries, but they don't work. I'm going to skip this and just say that look at the damage. So in any metal anode battery, if you charge at any reasonable rate, you form dendrites. Any irregularity forms a dendrite. And so the question is, can you stop that from happening either by a totally different SEI layer with different electrolytes? An approach that I'm taking is this one, that if you have a very thin membrane that has a very high Young's mod, which is high tensile strength, if it's so strong, the soft metal lithium can't actually make a dendrite. And so the idea is that if you deposit the lithium through this surface, you can prevent dendrites from happening. So we did a little test run of this, a little coin cell, lithium metal, and a conventional electrolyte with sulfur. And what we see is we see a pretty good response. This is very unusual to see a lithium metal sulfur battery have flat response. Now it finally died after 300 cycles, full cycles, but because there was a known interaction of the electrolyte with the lithium metal and sulfur. So now it just transfers the problem into how do you get some electrolyte that doesn't react with those ingredients. But from this, we are finding that the sulfides in the electrolyte do not get to the anode. Okay, so going right along, I'm just going to do one more thing. Electric vehicles do catch fire, and the ones in China are catching fire at some frequency. They're averaging 7 EVs catching fire a day, and so this has led to buildings getting very leery of that and not wanting to park EVs in cars. So, in any case, one last, if you indulge me 1 minute. Okay, this is in California. This is a duck-back curve. That thing around noon is that you're getting excess electricity at noontime because of solar. And so this is another graph of this work. Oops, I'm going the wrong way. More fires, duck-back curve. Okay. So at noontime, solar is turned on, that's the yellow, and we're actually moving energy out of California because we're making too much of it But very expensive batteries can be used to charge because the electricity free is noon. As the electricity at noon is free, and then you sell back at 3, 4, 5 o'clock where the real price is very high. And so you can actually sustain, use pretty expensive batteries, but what's the requirement of these batteries? They have to deliver its energy and also power, and they want power. And so for utility scale, and in order to do this delay thing, you need high power as well as a lot of storage. And that's an issue that I didn't really fully appreciate. So anyway, the last little thing is there's going to be competition for electricity. It's in compute. And whether compute is 20 or 30 or 40 or 50% of all electricity, I don't know. It's up for grabs. And that compute power is due to this machine learning and the queries. And there we're talking about several hundred megawatts per data center going to a half a gigawatt. And so you compare that to these little compute machines, 4 years old. That little girl probably, if it's raised by a family, a mother, father who speak different languages, they become fluent in those languages. By the age of 4, it can easily translate. If they're rich, they have a nanny, makes them speak a third language, gets 3 languages, can tell the difference between cats and dogs with much, much less data. This one doesn't have a child yet, that little lady, so anyway. And then on the upper right-hand side is a young lad doing gravity experiments, throwing food. And so this is machine learning, very, very fast, with very much less samples. And how much power? Well, these children are using 70 watts, of which half the energy is in their brain. 35 watts. But it's 35 watts, not 300 megawatts. So in the end, we actually need a better architecture. But with that, I'll stop. Thank you.